The birth of calculus, Newton, Leibniz, and the rise of modern mathematics. In the mid-1600s, Europe was in the midst of a scientific and intellectual awakening. Against this vibrant backdrop, a young English mathematician, Isaac Newton, was quietly beginning to unlock mysteries of the natural world. In 1666, while still a student, Newton sketched out the first steps of what would eventually become calculus, a new mathematical language that would permanently change the way scientists could understand motion, change, and the forces shaping the universe. In those early days, Newton called his invention the method of fluxions. He used it to solve problems about quantities that change continuously, like the way an apple falls from a tree, or the planets orbit the sun. For Newton, calculus wasn't just numbers on a page. It was a tool that could help him uncover the hidden laws of the universe. In Principia Mathematica, his landmark work published in 1687, Newton used his calculus-based methods, though he didn't call them that, to lay out a revolutionary view of physics, explaining gravity and the motion of planets in ways that were entirely new. But Newton was secretive and cautious. Despite his groundbreaking discoveries, he hesitated to publish his work on calculus. In fact, his first manuscript, De Analysi per Equationes Numero Terminorum Infinitus, written in the 1660s, wasn't shared widely. Instead, his mentor, Isaac Barrow, recognized the potential of Newton's ideas and forwarded a copy to a fellow mathematician, John Collins, describing Newton as an extraordinary genius, but Newton's reluctance to publish continued. Fearful of criticism and controversy, he held back, focusing on perfecting his theories in private. A rival in the making, Leibniz steps in. Meanwhile, on the continent, another brilliant mathematician, Gottfried Wilhelm Leibniz, was working independently on similar ideas. Leibniz approached calculus differently than Newton, focusing on symbols and rules that were easy to apply and understand. His system was elegant and clear, built around differentials and integrals, terms that are still used today. Leibniz published his work in 1684, and soon his notation became popular among mathematicians, especially in Europe. Unlike Newton's private approach, Leibniz shared his ideas broadly and was more than willing to collaborate. His notation, which used symbols like d for differentials, made calculus intuitive and accessible, giving it a foothold among scholars across the continent. While Leibniz's method was spreading, Newton was deep into his own research. His calculus was different, focused more on geometry and fluxions, how quantities flow and change. He used concepts of first and last ratios, a technique that aligns closely with the ideas of limits in modern calculus. But his methods were intricate and challenging to understand without explanation. The spark of controversy, calculus and the Royal Society. By the 1690s, tension was brewing. Newton had remained mostly silent about his calculus methods, while Leibniz had openly published and promoted his own. Some mathematicians in England, friends of Newton, began to grow suspicious. How could Leibniz's work resemble Newton's so closely without some knowledge of his work? In 1699, members of the Royal Society, an influential scientific group in England, started accusing Leibniz of plagiarism. The situation worsened in 1711 when the Royal Society conducted an official investigation into the origins of calculus. They sided with Newton, who, it turned out, had written the concluding remarks of the report under a pseudonym. In it, the Society accused Leibniz of stealing ideas from Newton, sparking a public dispute that raged until Leibniz's death in 1716. The affair left a bitter taste in the mathematical world, casting a shadow over the achievements of both men. A legacy of two notations. The debate didn't end with Leibniz's death. In fact, for decades, mathematicians on the European continent and in Britain continued to use different systems for calculus. British mathematicians, out of loyalty to Newton, stuck with his geometric approach and his fluxions. Meanwhile, most of Europe adopted Leibniz's system of differentials and integrals, finding it easier to use and more versatile for solving a broader range of problems. It wasn't until the 19th century that British mathematicians also adopted Leibniz's notation, finally bringing a sense of unity to calculus. Newton's other mathematical achievements. Beyond calculus, Newton's mind roamed across many mathematical fields. He introduced the generalized binomial theorem, making it possible to expand expressions with any exponent. He also developed Newton's method, an efficient approach for finding approximate solutions to equations, and made advancements in using infinite series, an area that fascinated him. His exploration of series was partly inspired by Simon Steven, a Dutch mathematician who promoted the use of decimals. Newton's work with power series became a critical tool for later mathematicians, and his contributions to areas like the harmonic series would pave the way for future discoveries. In the end, to giants of calculus, the story of calculus is not just about who discovered it first, but about how two mathematical giants, Newton and Leibniz, unwittingly shaped a new era in science. Newton's insights were groundbreaking, driven by a need to understand the natural world through mathematics. Leibniz brought an elegance and practicality that would make calculus accessible to future generations. Their rivalry, though unfortunate, sparked discussions and innovations that pushed mathematics forward. Today, calculus is a universal language for scientists and engineers, a fitting tribute to the vision of both Newton and Leibniz.